This is Lucy. She's a working cocker spaniel and she loves to run. When I'm out for a walk with her, she explores the fields and often comes back to check in with me. And it made me wonder how much distance she actually covers. I decided to make a device that could track her journey so I could analyse the data.
Sit. Good girl. Break.
I started off with the building blocks I would need to create the tracking device. A GPS receiver to fix the location on Earth, a microprocessor to manage the data, and some form of data storage to keep a log of the route travelled. Of course, all of these devices would need to be powered. The dog needs to carry all of this equipment around without hampering it, and I was aiming to fit all of the electronics onto her collar. So although this was a technical solution, it was clearly not optimal. I needed to specify some better components. Instead of the Neo 6 GPS circuit board, I used a Baishan BE122, which was tiny by comparison. I found an OpenLog serial data logger board that would combine both the functions of the microprocessor and data storage, as it had an 80MB328 built in, which would automatically dump the data it received onto the micro SD card. Instead of using these huge lithium-ion cells, I would opt for a small 120 mAh LiPo battery running at 3.7 volts. This was a great choice as I could power the circuit boards directly without any voltage conversion. The U-Blocks company designs chips that make use of global navigation satellite systems, and they provide a piece of software to help you evaluate their products called U-Center. You can download the software from here. The receiver needs to be connected to the computer via a serial port, so the easiest way to do this is to use an FTDI device with a USB connection. The circuit is very simple to wire up. Once plugged into the computer, the device takes a bit of time to get a fix on its location and will start to flash its red LED once it starts transmitting data over the serial port. Load the U-Center software and configure the settings. The connection will be through one of the COM ports, and the baud rate for this particular device is 38,400. As soon as the serial communication starts to take place, the U-Center software will use it and display a range of information in different formats. Let's have a look at the first display panel, which shows a map view. I am based in the Midlands of the UK, so you can see that the device has correctly located my position. The second panel shows the signals being received from individual satellites. You can see here that the signals are being received from the American GPS and the Chinese Baidu constellations. The next panel shows the detailed coordinates, including the elevation of the receiver. This panel is a histogram of the satellite signals. The data being received in binary form, the data inside each packet, a deviation map. Ideally, if you're in a fixed position, this map should show a small amount of variation over time. And finally, a sky map of the satellites and their positions overhead. You can have some fun exploring these different options and review the performance of your receiver over time. The default sample rate for the receiver is 1 Hz, so it takes a sample of my location every second. This rate would be fine if I was using it to track myself on a walk, but I wanted to track my spaniel, who darts backwards and forwards quickly, so I thought I would change the sample rate to 5 Hz to see how that worked. As we're using the U-Center software to communicate with our device, it is easy to change the settings while it's still connected. Let's have a look at how to do that. Oh, by the way, in this view you can see that the receiver has now picked up Galileo, the European constellation. From the top menu bar, choose View, then Messages View. Choose the config setting, then scroll down to the rate setting. The measurement period needs to be set to 200 milliseconds. This will give a sample rate of 5 Hz. Don't forget to send the settings to the serial port using the button at the bottom. If you look at the animation, you can see the refresh rate has now changed, as they are updating faster. Great. I now know that the device works and is receiving accurate data, so I need to design and build a prototype. I decided to put the circuit together on a breadboard in case I needed to make some more adjustments to the firmware before I was finally ready to solder it all together. A key part of the design and build process should include some thorough testing. The first test I completed was to put this circuit on my garden table for 10 minutes to make sure that the GPS data was being stored on the micro SD card. It worked flawlessly, so I decided to do some more field testing. The first test was a walk around my local park. This test was simply to walk around the outside track. I collected the data on the SD card and loaded it onto my computer. We need to convert the file type from a TXT file to an NMEA file. This is a standard format for GPS files and stands for the National Marine Electronics Association. Once we have the NMEA file, we can simply drop it into Google Earth. Google Earth does a great job of filtering out the good data to show the track. As you can see from this image, the device has accurately tracked the path around the park. The data jumps around a bit at the beginning as it gets a fix on the location, but then its positional accuracy is very impressive. I thought about emulating my dog's motion with lots of to and fro type movements, and I decided to walk around the park in a zigzag-like motion. I converted the second plot to an NMEA file, and it looks like it has again plotted the perimeter of the field. It's only when you zoom in you can see the fine resolution of the path, and it has clearly captured my erratic route. I think these results are excellent.
Ready to go for a walk, Lucy? Ready? Wait. Look. Look. Walk on. Wait. Brake.
My final test would be located in a small area of woodland that had some tree cover. I was interested to find out if the satellite signals would be degraded due to the tree canopies, which were in full leaf. It takes about a minute to get a fix on the location from a cold start, but I can see the red LED flashing, so I know it is sending the location data over the serial link. If we look at the data logger board, you can see the orange LED flashing, which shows that the serial link is receiving data. We're good to go. This
Bee's nest. Hello, good girl. Who have you found? Hello, hello. Morning.
This third test shows another good data capture with no degradation under the tree canopy. This means that I can use the device in dense woodland cover. I'm very impressed with this little receiver. It costs around £5 plus delivery on AliExpress. Now that the first stage of testing is complete, I can build the device into the collar and give it a trial run. The connections are quite simple, so I soldered the wires and plugged in the battery to give it a final check. The receiver is working as the LED is flashing, and so is the data logger. This is one of those cheap light-up collars that has a flashing LED that lights up a tube inside the double layer of the collar material. This is used for dogs when they're walking at night time. I originally thought I would place all of the components inside this collar to keep them protected, but it was a bit too fiddly to thread them inside. As I wanted easy access to the battery connector and also be able to remove the micro SD card, I decided to encase the components inside some heat shrink instead. I had already adjusted the collar so that it was a good fit for my dog, and then I laid out the components onto the collar to check that they would all fit. A bit of clear heat shrink completed the task, but I just had to cut some slots to access the battery connection and removal of the SD card. So, this is the big field trial. I connect up the battery and wait for it to get a fix.
I can see that flashing in the back there. So I just need to get a fix on this, and it will be fixed when that starts flashing red. I'll just leave that there for a few seconds.
I will also be logging the route using my Garmin handheld GPS. The collar now has a location fix as the red LED is flashing, so I just need to put the collar on her and we can go for a walk.
Right, you're gonna. Right, there we go. Okay. Brake. Good girl, walk on. Good girl. Lucy.
This set of data is uploaded to Google Earth, and when we zoom in you can see the track that has been logged as Lucy runs around. You can see from the blue line that she keeps coming back to check in. She also explores different areas of the woodland and diverts from the path. There's a particular There's a particularly energetic track when she meets a Labrador and they had a run around in circles for a while as they played. I'm going to overlay the route logged by the Garmin GPS that I took around the forest and change the properties of this track to red. My route has been logged at a lower sample rate and you can see a much more direct path. It's possible to look at the properties of this data and find the total distance covered inside the Measurements tab. Of course, we can do a flyby of the route in Google Earth using this button, starting at the car park. I should note that there were not any sheep in the fields when I was testing this. They just appear in this Google Earth image at the time the overhead photo was taken. Logging this data has been a real success. As we fly over the route, it's easy to see the difference between the two tracks in terms of the distance covered. This data can also be exported as a CSV file. I saved it and loaded it into a spreadsheet. From there, it's easy to sort the data on a column, and I found that Lucy had a top speed of 37 kilometers per hour. So, to summarise, let's look at the statistics for human versus dog. My dog travels at least twice as far as I do, and her top speed is about 7 times faster than my walking pace.